Okay, hello guys, we're starting the third lecture, numbers and names. Okay.
Okay.
Today we'll talk on something a little off of the previous things. We'll talk on the implementations or usage of the numbers. Maybe something that you didn't know, or maybe you heard something, but we'll see. We'll see. First of all, let's talk about something that is called choice.
Choice?
Choice or
Choice.
or randomness. Something that happens in a random way that you don't know how it happened actually at all. Like for example, you flip the coin. You flip the coin, right? And how it will fall? Head or tails?
We don't know.
So do you know or you don't?
We don't.
You don't.
It's totally random.
Why actually? Why? Oh, okay. When we talk about not maybe coin, but about like it's called in Russian, it's buterbrod, butter with bread. What do you think? How it will fall?
I don't know.
With butter or no butter?
We don't know.
There is a saying that sandwich with butter falls mostly on butter side, and actually that's true because what do you think? If you talk about, you see the bread, right? Right?
Yeah.
And there's a butter layer on it, right? So which side, this or this? What do you think? Which side is heavier?
The butter side. Yeah.
Which one?
The butter side.
With the butter side, yes. So actually, because it's heavier, it's usually falls on this side. And not only because of this, the other thing is that when it falls, really, you know, it can jump and falls on the other side, right? When you drop this sandwich, right? So when it falls on the butter side, what it does with the floor? It sticks to it.
Yeah. I have a
And it's not jumping anymore and cannot turn anymore. So more often this sandwich falls on butter. Okay, so what's the question?
Would it tip over to the buttery side because since it's heavier, it will tip it in a way that the heavier spot is facing the ground?
Oh, no. You flip like this. You flip this thing like a coin, right? So it's rotating. You don't know how it will fall down, but when it falls, right? When it falls, the heavier part usually force it to fall on the heavier side. One thing, and another thing is that it sticks. The butter sticks. So when you really drop the sandwich, right? So it will fall not symmetrically. So if you look at it, it's the situation is a little different than you flip a coin. So why I'm talking about this? Because situation is not. Do you know the word symmetry, right? It's not similar. You know, one side is very different from the other side.
Yeah,
and in the coin, they actually identical, right? The picture on it doesn't actually matter. It's very slight. Okay. So the same thing in other things. Randomness usually happens in the situations when the situation is very symmetrical. You cannot really choose before which result you will see. You study the situation. When you see that it's really symmetrical, there is no way that one comes more often than another, then probably it will be random. But you not even actually know in reality. You should repeat and repeat and repeat, and you will see that it's random when, like for example, the coin, like when you flip it, right? Maybe five times it's head, five times it tails, right? Or something like this. But usually it's rarely happen 5 and 5. Usually, but when you or then you drop it many times, then maybe at the levels like 1,000, right? You may will have like 1,000 maybe and 3, and here will be 1,010. So these are pretty close, right?
Yeah.
But if you drop it like 5 times, that would not be like 5 and 5. 5 and 5 will be rare. Maybe 5 and 3, maybe, or something like this. So the randomness comes with the big numbers. The bigger number, you will see is it random situation, random or not. Now, how mathematicians go with randomness? There is a theory which is called theory of probability.
Oh yeah, Papa has a book on that.
Yeah, theory of probability. So what it does, this theory, actually it can say, it works with probabilities, exactly. So the choices, right, for example. So for example, with the coin, how many choices we have? How many results can we get?
2.
Just only 2.
Yes.
Can it just like fell like this? What do you think?
It can.
And stop.
No, because if it does, it will fall over to one side.
Yeah, usually on that side, yes. When the surface is hard, right? But when it's like sand, right? When it's sand, it can actually do that. In this case, we should consider at least 3 choices, or maybe more. Okay. So yes, but when the surface is hard, there is only 2 choices. It cannot stand like this. It will be this or this way, right? Heads or tails, right? So we have 2 choices, right? 2 choices. And one of choices actually you see. You flip it, it comes. Now what mathematicians do, they have this term probability. They're talking about probability, they say this, that probability, when you have 2 choices, probability usually it's calculated like 1 divided by 2. Why divided by 2? Because there are 2 choices, and 2 choices together creates 1, right?
Yeah.
It's the whole thing. And this is half thing. So this way or that way. So it's a half, right? So
Yeah.
so that's why they why they call it one this fraction, right?
50-50.
Yeah, half. Yeah, 50-50, right? If you have, okay, for example, if you have 100 choices, how can be 100 choices? For example, there is something that is falling from the very high tower, right? For example, somebody standing on the tower and throwing the ball, like 100 meters tower, right? And here you have 100 baskets. 100 baskets.
Yeah.
And you drop the ball. Which will be the probability? The ball will drop like something, usually like pretty good enough to put into some of the basket at least.
Yeah.
At some of the basket. So what will be probability? What do you think? That ball will fall into this particular basket. You choose it before.
100. 1%.
1%, right? So that's 100 chances, right? How they talk about chances, right? 100 chances, and only 1 chance is that we actually need. The chance that it falls into this basket A, right?
Yeah.
So it will be, the probability will be 1/8. Okay. How do you pronounce it, by the way? 100, right?
Or 100.
Okay. Now let's talk about another thing. Let's understand that we have like we choose not only 1 basket but 2 baskets. This basket and basket A and basket B.
2%.
Yeah, 2%. So for 2 baskets, 200, right?
Uh-huh.
Now next thing. Let's. So when you have this choices A or B, actually the probabilities add to each other, right? In this simple choice. Let's talk about little a little more complicated thing. Let's, for example, we're flipping two coins. Two coins. And we want to count one probability that two coins fell down right both with the heads. Both heads. How to calculate this probability? The easiest way, well, you may talk about how many choices do we have here? What do you think?
4 chances.
Huh?
We have 4 chances.
Oh, 4 chances, you know, really? Okay. So red left head will be like 1, okay? And tail will be 0. So we have
The probability is 25%.
1 and 1, 1 and 0, 0, 1, or 0 and 0. 4 choices. Okay, you told me I got it, I heard it. Good.
25%.
Good. Okay, so we need only this, right? 1 of 4. Probability is 1/4.
Which is 25%.
Yeah, 25% if you talk about, but probabilities usually goes like this. It's 1/4. Or you may say 25 chances of 100 or whatever, or 25%, like you said, right? But usually it's used like this. And the other thing, like for example, if we want to find out of this thing that, for example, just one of these coins will be, like for example, tail. How many choices do we have?
For tails we have 1, 2, 3, 4 choices. And yeah, and same thing for heads.
One of them. Just one. This or this? Again, or but a little different.
Tails, tail.
This is tail, so tail, right?
Yeah.
This one. This is tail, so it's tail. 2. This one is tail, so 3. And there are no tails.
Oh, so 3.
So 3 of 4, right? So this probability is 3, 4. Something like this.
Yeah. And same thing with heads. 3/4, 75%. Yeah.
75 here.
Yeah. Oh yeah, that makes sense. Okay. Yeah, 74.
Or you may count in a different way. You have only one choice that they are both coincides, that there are both heads, right? There are no tails in this, right? So all of the rest will be tails. One of them will be tails. So we calculate it like this. P is 1, which is the 100% minus 1/4, which is this, right? This is the probability of this 1/4. So 1/4, and there is 3/4.
Wait, but why would it be minus 1/4?
Because the whole thing is 1.
Quarter.
Always. All the choices are 1. It's 1. And we're dividing it, right? We're dividing it. So we know that only in this case we don't have tails. In other, whatever they are, we have tails. Only in this case we don't have tails. So we subtract 1/4 from 1. This 1/4 subtract from 1. From the whole.
Yeah.
That's all. So that's like basic things, just for you to understand how probability works, okay? So in probabilities, so usually if we're talking about probabilities, usually it means like that probability 1, it means that the event will happen or not happen. What do you think? Probability 1.
But it will happen.
It will happen, always, right?
Yeah.
And probability 0?
It won't happen.
Never, right? Still, probability has interesting things like paradoxes, like everywhere. Like for example, imagine that we're dropping the ball, a very small ball, like we call mathematical point ball.
Oh, did
Uh-huh.
I know it's a paradox.
Okay.
Because
you know everything. Okay, just wait.
Because points don't have size.
Okay, I explained a little. Okay. So you're dropping point on this certain interval, right? How many points are on this interval? Actually, there are infinite points.
You get infinite amount.
Infinite amount. So how many choices we have? Infinite,
Yeah,
right? Infinite. So if we want to calculate probability to that this point comes right to this point, to point of A, the probability will be easily, you calculate it, it's 1 divided into infinity, right? So it's something like 0. So it will never happen.
What?
It's never happened. But you dropped it, right? You dropped it, so it will fall. You know it will fall, right? You dropped it somewhere here. You can put like walls like this, right? So it will fall, no problem. So it will fall to one of the points, and still the probability for any of these points, it's still 0.
How?
Just this simple calculation: 1 divided by infinity.
Is close to 0. How? Because the greater the denominator gets, the closer it gets to infinity, which means it's 0.
Yeah.
Because infinity
1 divided by infinity, it is 0 actually.
Okay.
So this is something that just for you to understand. The probability is very nice, but it has certain paradoxes. So just beware of this. Okay. So certain things are you can think about it in your idle time about all this. Okay. Now let's go a little further. So one of usages of the numbers, right? The other usage, and very important one, it is called information. And probably you heard, or maybe not, that information is measured in
Teaspoons?
what's the measure unit for information?
I don't know. Oh, sorry.
Bit.
Oh, feet.
Bits.
Oh, bits.
Bits.
Eat.
Oh, bits. Is it? Oh, bits.
Bit.
Oh,
Bit.
that's for computers.
Yeah, that's not that. Okay. So information. Okay. What is information? Okay. Again,
Zit.
imagine that you're flipping a coin.
Zit. Huh? Sorry.
Imagine that you're flipping a coin. And before you flip the coin, you don't know, because it's symmetrical, right? Both sides are symmetrical. And you don't know really how it will fall. Head or tails. If you really don't know, right, and then the event happens, right? The coin fell down, right? You see, for example, it fell on head. In this case, it is defined in mathematics that in this case, when you have two choices, again, two choices, and only one result, and you got this result, you got this information, it's called 1 bit. Whatever it falls on any side, head or tail, anyway, you know. Before you didn't know, after the event, you know. You got information. And information is 1 bit.
Papa, you know, Dida?
Yes.
Dida, for example, a byte is 8 bits. So that's technically, so it holds more space for more information to be held into it. For example, if you flipped 8 coins, it can hold that much information in it about what you got as a conclusion. Whenever I'm gonna hear somebody say bit now,
You may. Okay.
Zits.
You may think about it, but it's like, for example, if you drop 1 coin, you flip 1 coin, right, and then another coin. How much information you get?
You got 1 information. 1 piece of information. Oh wait, 2. Yeah, 2.
2.
Yeah,
Okay.
there's 2 coins.
Yeah. And how they write these bits? They write it in binary system. Remember this binary, where only 2 only two letters, 0 and 1, only two numbers.
Yeah.
Right? So write it in this way. They write, like for example, one result, right? You write 1 bit. It will be 0 or 1. And you write 0 or 1 here. Like for example, 0.
Mm-hmm.
This is called first bit. First bit. Then, if you talk about a little more, there's another one. For example, it's 1. There's a second bit.
Uh-huh.
And there it goes. Lower bit, higher bits. I write like a binary number information. Okay. What I want to say about information too, a little more. Information is a very interesting thing. Information is actually a measure of, you can call order. And the opposite to order is another thing, what is called chaos.
Cows?
Chaos is totally random situation, the whole mess. Everything is messed up. This is chaos. And order, it's a very interesting thing because nobody knows what order means. Like for one person, like on his working table, this is order, but another person comes and say, what a chaos is that you have on the table? Like your mother can come to your father's table and say, what a mess you have on the table. But it's a working order for your father. Okay? So order is a very, very relative thing. For order is something that you decide before anything. You say, just say, okay, this will be my order of things. I put it like this. Okay? All the rest is out of order. And now what happens? For example, imagine that you have a room, right? And you decided, you put into this room many, like for example, many marbles. And you put all the marbles into one corner. Like for example, 10 marbles, right? For example.
One corner.
In one corner.
That's neat. That's neat.
And you call this order. This is my order. It's up to you. For huh?
It's neat.
Say it again?
Neat. It's neat. I like it. It's neat. I also like it.
Okay. For other person, order will be maybe other corner, or maybe put marbles like this here, right? Or maybe diagonally. Or any other. Or maybe in the star. You know, like star.
Yeah.
Right?
At the top right corner.
So there could be many different types of order, right? So these marbles you can put in different ways. So for example, let it be order like this, right? That you put everything into the corner, right? And now what you do, you take this box, it's a room or box, whatever, and you shake it like hell, right? So what will happen here? What do you think?
The marbles will be everywhere.
Right, everywhere. But everywhere how?
Huh?
Can they be like, for example, can these bubbles be after that you shake it like this? Like in square, you know, like in square.
No.
Can they be in the line maybe?
No, I think.
Can they be in this line?
No.
Can they be in the star?
No, but there's also still a very slim chance.
So there's an interesting thing. Why they don't come into this thing, right? Why? Why they never see the star or whatever, or even the line? But what you see actually, it's like what is called actually random. It is chaos here. And each time you shake, the chaos is different, right? Each time. So many. Why this happens? Why do you think?
Well, because if you put it in one spot, if you shake it up, they will be bound to go everywhere. That's my opinion.
It's again, it's about probability and randomness. You understand, right? So order, it means that you put some, actually what order usually means, that there is some information written here. Something happened. Before everything, you put everything here. You set it in a certain positions, right? But when you shake it hardly, what happens actually? There are very many possible positions for each marble in the box.
Into a heart.
Like many. So there's for each marble amount of positions. Like for example, is like, I don't know, maybe the size of it. Like if you like 100, right? And here is like maybe 50, right? And one is the size of marble, for example, right? So how many would be here positions for each marble?
50 positions.
No, 50 here and 100 here. So how many totally?
150.
You can calculate it like this, right? Like make it like this, right?
Oh wait, no.
So 50 rows and 100.
Oh no, I'm stupid.
So how many?
5,000.
How many positions will be? Huh? 5,000.
5,000.
5,000.
5,000. Sorry.
5,000, right? So probability for each marble to be in any place will be 5,000. So the probability that the marble will come here, right, at 1 divided by 5,000. It's a very low number, right?
Extremely.
So probably it will be in any other place, but not here. The same thing you may talk about any particular point, like you choose this point, right? And probability that marble will end here, like for example, this point is the top of the star, right? Top of the star, which is probability that one of the marbles will go here, 5,000. And for other marbles is the same, it's very low. So the theory of probability says actually that after shaking, it will go in any other place except something that you already chosen for these marbles to be.
Oh yeah, this is very simple.
So whatever order you put, the marble will never go there. Very rare. So order is very interesting thing. But if it comes here, for example, not in any other place, the probability is 1/5,000, right? You get a lots of information about this. Remember, information is somehow connected with the randomness, and actually there's a formula that actually gives the amount of information, and the formula is like this. Maybe you sometime learn what it is. So this information, how we call information, L, for example, it's logarithm. If you heard about this, maybe not.
I have. Yeah.
1 divided by p, where p is probability. To the basis of 2. Why 2? Because it's based on binary system. It may be other thing than you use, not binary system, but another system. So 2, it's about binary. So 1 divided by p. P is 1 divided by 5,000. So it will be logarithm of 5,000. That's pretty big. Not that big, but pretty big information that you get from here. And just to explain what logarithm is, this is a function, and the logarithm function means that it is the value of the power that you apply to 2 to this basis.
Yeah.
To get this 1p, to get 5,000. So 2 to the power this will be our thing. So this is okay. So I wouldn't use it. That's a little, that's confusing. So this is our amount of information. I won't calculate. You can calculate on your calculator, right? You get calculator, you will know what kind of information you get from this. Okay? In this case, the same amount of information you get when other marbles come to particular points of the star, right? Whatever they are, depending on how many marbles and everything. So you can count this information. So this is another application of numbers. Just for you to know to get some example of what numbers. Any questions for now?
Logarithm.
What's logarithm?
It's the inverse of power. Actually, no, it's not an inverse of power.
What's that?
It doesn't. It's not a.
What does the LG mean?
Logarithm.
What does logarithm mean? I think I've heard of that term.
This is a function. Again, okay. Imagine that you. Okay. What's the term for this? 2 by power of something, right? To the power of like W, right? For example. And you have something like n. 2 to the power W, you get n, right? So logarithm 2 of n it's the power. It's the power that you use to get this n from 2.
Oh, okay, I understand. Oh wait, doesn't n mean any number?
Yeah, those are numbers.
That's positive, right?
We're not really talking about logarithms here. Just mention it just for you to understand. Logarithm is so-called inverse function of the power function. 2 to the power of W. It's inverse to that.
The opposite.
Oh, opposite, yeah. It's called, yeah. Not opposite, I think the term is inverse, I think, still. It's not the opposite function, so inverse.
Right, it is inverse. Yeah, Texas was asking what inverse was.
Yeah. So just turn it over from inside out. But it's just, you may talk on this later, talk to your papa and whatever about this. We're not talking about this right now. So this is logarithm, right? So now we continue a little further. We remember that what we were doing, like when we see this counting, right? 1 equals 1 equals 1, right? So we go from one to another one, to another one, to another one. And we talked that this is actually, this pairing, actually it is the same as adding, right? It's plus 1, this is pair of 2, this is pair of 3, so plus 2, and so, and further on, right? And we see certain of the word like symmetry between one and the other one, right? The two sides are almost the same, right? So you may flip like a coin it back, like put this one here and this here, it will be exactly the same, right?
Yeah.
So it's symmetrical picture, right? The same thing is if you're going further, it's pretty symmetrical. So the other.
Last time you told this to us. Todd. It was just saying.
Okay, so this is why symmetry. Why I'm talking about this? Just that you see that symmetry is even in this simple ways like we count things. As we count, we're using certain symmetry of things. All the trees are symmetrical, similar. Symmetry is very close to similarity, very close. But the term symmetry, it implies that the things are not only equal, they're not just similar, but they are different too. So they have like this thing, remember this uniqueness, right, and identity, right? So symmetry is about this. So, like for example, we have this coin, right? We have coin. We have the head, right? And we have the tail, right? I don't know whatever the tail. Pitches are different, right?
Yeah.
But the coin itself, if you don't really care about pitches, but the real like weight of the coin, format, like everything, it's very similar. That's why when you flip the coin, it falls with the same probability on head or tails, right? They are symmetrical. So they say that the coin is symmetrical on their sides. So you may flip the coin this way or turn the coin this way or that way. It's just looks the same, except the pictures. Pictures are just to distinguish one side from another. The other symmetry thing is like the other symmetry. This is symmetry maybe of flipping, right? Flip symmetry. Another symmetry is like you have a big tree and small tree, and you have a bigger tree. They are very similar, right? But they are different at the same time. So what is this?
Yeah.
This is symmetry of scale. So we change the size, right? And it's still called symmetry. Now other thing, we have a car, right? And the car moves from point A to point B. It's the same car, but in different positions, right?
Yeah. Yeah.
And this is called, you may call it position symmetry, but usually they call it shift symmetry.
Shift?
Shift.
Oh, the same thing.
So shift. We shifted.
It's the same thing like this. Points, for example, a wave, and there's a bunch of points in the wave. They move, but they're still the same points.
Yeah, that's right. Good. There are many, really many symmetries. Like wave, yes, wave, one of the symmetries. Another symmetry is like you have Earth, right? And like ancient people thought that the star, well, they actually thought even not like this, but anyways, that the sun is rotating around Earth.
Oh yeah, Mama told us.
And again, when it rotates, it comes to the certain position again, right? And by the way, do you know how many time will pass until the sun will come to the same position in the sky? How many time it will take?
What?
You have some position in the sky, right? Like there. You measure this position, and then you wait until sun will come to this position. How much time will pass? What do you think?
It depends on where you are.
No.
It depends on how far the star is.
Okay. Okay, 2 clues now. The third clue, okay? It's not clue, third guess. Any clue? Oh!
Doesn't come up.
So how many time?
Once a day.
Huh? 1 day?
Once a day.
What do you mean 1 day? We see it already. It's there.
The sun's always up.
And?
Oh, it's always up. It's always up.
Okay, not up, not certain position in the sky. Exact position.
Yes, it is. It is just a different part of the earth.
When the sun will come to the same exact position.
24 hours.
Huh?
24 hours.
No. 24 hours. It will be so close, but not in the same position. A correct question is never, but it will come to much closer position in 1 year. 1 year. Remember, Earth is rotating around sun too. It's not only rotating around its axis, it's rotating around the sun too. So the sun will be at the same position in 1 year, and still it will not be the same exactly. So actually it never happens. But anyway, so you understand that this is called it is called symmetry of rotation. The same thing like rotation Earth, right? 24 hours, you named this number, right? This number is like rotation of the Earth around its axis, right? 24 hours, Earth will come to the same position to itself. So it is symmetry of rotation. And there are many other symmetries. Like for example, the numbers, right? And there's even general understanding of symmetry. The symmetry in general it means that anything changes, but something is preserving. So there's change, something changed to something, right? But still in this process, something is preserved. Something is still similar. That's it. If something changed but something still similar, so things are different and unique in a certain way. So not similar and unique in the same way. This is called symmetry. Like for example, one of the interesting things, probably you heard about it. This is called energy conservation law. Energy conservation law.
Energy
Conservation.
Conversation.
Oh, no, okay, I'll write it. Conservation. It's preserve. Conservation. It means that energy, whatever you do, energy is still the same in the physical system. So, like for example, you stand on the floor and jumps. You're jumping, right? You're jumping, but your energy it's still the same. Right there are different types of energy. There's like they call potential energy here, then kinetic energy here, but energy is still the same. So you're jumping like a wave. You mentioned the wave, right? Wave goes up and down, but the energy is still the same.
Can I explain?
And this is symmetry. Yes, sure.
Potential energy is usually energy waiting to be used, or the height.
Yeah.
Kinetic energy is the energy that's being used.
Kinetic energy, close, not exactly. Kinetic, it's the energy of movement, right? So when you're really moving, you have kinetic energy. If you're just preparing to jump, right, you have potential energy, something like this. There are other forms of energy, like thermal energy, where something is hot, like a tea in the kettle, right? It has lots of energy. Believe it or not, but heat is a huge amount of energy. That's why we have all the engines, which are actually engines that burns the fuel, right? And that's why, and it's transformed into kinetic energy, which is energy of movement of the car and whatever. So why I meant it, because this is again about symmetry. The situation changes, like in the wave, goes up and down, right? But the energy is still the same. Same things everywhere. Yes?
Is it heat when the atoms move around extremely fast, which make huge amounts of energy when they move, and then and then we can feel it?
Exactly. Like we have air, right, in our room, right? Temperature in our room, like for now, it's 23 Celsius, right? With this temperature, the atoms and molecules of the air, right, are traveling in different directions randomly with a very high speed. The heat speeds are about 1 kilometer per second. It's very close to the first, this cosmic velocity.
Okay, Dita, but I have a question.
Yeah.
Wouldn't the atoms impale us?
What?
Wouldn't the atoms? Dita?
Yes.
Wouldn't the atoms impale us? Hurt us?
Something I don't understand. Antosha, maybe you can tell. What's
Would the moving atoms hurt us?
What the moving atoms?
Veritas.
This really depends.
Can you rephrase the question? Okay.
Cause any damage to moving atoms?
What damage to moving atoms?
Do the moving atoms cause any damage? To
Oh,
us?
moving atoms, of course they do. Yeah, these high speeds, right? By the way, some of the atoms can have even the speed of the first cosmic speed, 7 kilometers per second. So it can go out to space. And some of them they do. With that high speed, right? With this high speed, they do a lot of actually damage to anything. Like for example, your glass in the window, right? Glass in the window. It's bombarded by the air molecules all the time. And believe it or not, but glass is very hard material. It's actually 100 times is more strong than steel. Believe it or not.
Really?
Yes, really. Yes.
No.
Glass. Yes, glass. It's fragile, right? It's fragile, but it's fragile. That's fragile because it's very hard. It's a strong material. So the atoms heat it, and they very often they penetrates into the glass, and when penetrates, they cause this cracks, small mini microscopic cracks in the glass, everywhere on the surface of the glass. Some of the atoms travel further, so they have like it's called defects in the glass. Okay. So when time passes, right, these cracks, because they continue bombarded by the air molecules, they become bigger and bigger, and the defects, the empty spaces filled with the air molecules somewhere inside the glass, they come closer, and there are many of them. At a certain point, they connect together, and they create a big crack, and the glass just broken. The glass cracks. It cracks, nobody knows when, but it can be calculated. It is called, in English, усталость. Как это будет, Антош?
I don't know.
Ну, по-русски усталость, по-английски как будет усталость?
Exhaustion?
Tiredness or something, yeah. Maybe tiredness. Something like that. Tiredness of materials. So materials are actually become at certain time, nothing happens, but they become tired, so-called tired. They're very close to breaking. And at certain point they just break. So yes, they do. The answer is yes, they do damage.
The atoms do cause damage.
Yeah.
Give it to us?
Yes, even to you.
To us too, yes, but biological organisms, they know how to fight it. You know, we always repair ourselves. You know how many times like our DNA repairs itself?
How many times?
I don't remember, but you can find it. It's lots. Like 1,000 times maybe per minute or something. And DNA is very conservative, right? It stays without changes. But still, because the repair process is very good, very well designed, right? So it's repaired all the time, and still sometimes we have these called mutations, right? So that's mutants are born, or just person can die. Okay, so just a little about about continue with the symmetry. Okay, symmetry, just to understand what mathematics do with these things. Mathematics speak about symmetry in terms of so-called groups. Groups is a number, actually it's a collective, some collection, right? Or set of some objects. Usually they're called transformations. Oh.
Isn't there sets rational numbers, irrational numbers?
There are lots of sets. There are lots of sets. Set is just some many things of similar type, right? But the group is something else. The group is a set or collection of certain things, usually transformations, the transformations of symmetry, so symmetry transformations. together, but not only transformations, but the way how to combine these transformations into each other together. It's called group operation. Group operation. What is this? Like, for example, one thing is transformed into another thing, right? And this way of transformation we name like for this, like A. Just we call it because it's just a name. So it's somehow process transformed into this. Okay, like A transformed into B, right? And we call this A, this small a. These are capitals. Right? Now we can think about transformations back from B to A. Okay? And this is called inverse transformation.
Yeah.
And also we can think about going A, and we call it like inverse transformation, like it's B, right? And when we go to this way and back, we return to the same state A, right?
Yeah.
From A to B, then like from A to B, and then again to A. It's the same, right? This same transformation, which does not change the thing, it is called group unit, or E. Usually, it's like one. I wouldn't go too far. It's like E. Okay, so E is group unit, which does not change the situation. So now, because we named this transformation A and this B, we can write it like this. A transforms through A small, and then it comes to B. Or back, B using B transforms to A. So it goes like this. You read like this: A, B, 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 A. You may put arrows here, but arrows may be omitted too. So A and B are process transformations. And now we call this group operation, which combines one transformation to another. How? Pretty easy. If we have E, we write it like this: AB equals E. It's like multiplication, written like multiplication, but it is group operation. It means you read it like this. You first apply transformation A, then apply transformation B, and you come to transformation E. So group is a set or collection of things, of usually transformations, symmetry transformations, and inverse elements, and group operation, and the element E. And we will see how it goes right now. The simplest group is group that consists with only one element, E. That changes nothing. Transformation 1 to 1, like this, equals. So it's E. So you can combine these two, E and D, and still be E. You combine many of E.
Also, it's like one. It's like one.
Exactly. If you talk about multiplication in numbers, right? So it is a group of elements, numbers, with the operation is multiplication. So it's 1 multiplied by 1 by 1 by 1. Or other group is addition group. This is multiplication group. And addition group is 0 plus 0 plus 0. This is group operation. This is group operation. So all these are group operations. Group operations. So there are different types of group. This is group of addition. This is group of multiplication in numbers. But here it's just some abstract transformations. E, right? Let's add one more element, whatever it be. Let's call it A. So we have a group of two elements, E and A, right? E does not change anything, so we may write A. Oh, sorry, I won't use this. A and D. E and A equals A. It's like multiplication to 1, right?
Yeah.
A. That's okay. Now what about A? We can multiply A to A.
Which equals A squared.
Yeah, A squared.
In this context, it would probably equal A.
Can it be like A again? Like for example, A squared, right? A by A, right? What should it be? It should be equal to something here, the same group.
A.
The group is so-called conserved. It's not like in one can. In one can and nobody comes out. So A by A.
A.
Can it be A?
Yeah.
It cannot be A square because there's no A square here, right? So it should be this or this. So the choice is only two. So you suggest A?
Yeah.
But it means that A this, what is this? Is A,
Times A equals A.
so it means that A should be equal to E,
Yeah, it should.
but it's not. It's different. They are different things. So it cannot be A.
Different variables can equal the same thing.
It cannot be A because
Not in this case.
yeah, if we take this case, right? A squared equals A, it means that
Different rules here.
A multiplied by A, right? And in this case is A by A equals A. It means that A should be E, nothing else. But A is not E, so this cannot be simply. This cannot be. So
Maybe
the other
E
choice, huh?
Maybe it could equal to AE.
There's only choice. We tried A, it's not coming out. We may try E.
Oh yeah. But that still wouldn't make sense because then it still means A would equal E. Because if E times E times E equals E, A squared equals A there for A is still equal to E.
Example, I will give you the example of this. You understand easily. E, like for example, multiplication group which consists only of 1 and minus 1. So E is 1, right?
Oh yeah, A squared.
And
Minus 1 times minus 1 equals. Oh yeah. Oh yeah.
you see, this is one of the examples of that group.
Did that.
Yeah.
Did that.
Oh,
Yes. A cubed equals A. Yeah, of course.
A cube.
Yeah.
Okay, let's try. A squared equals
cubed
E.
times E also
A
equals
cubed means A squared, A, right? A squared is E, E, A. Exactly.
Very good, Vita.
Very good. These groups, which consist of finite amount of elements, they're called finite groups. And what you see in finite groups, so if you continue to multiply to apply this group operation again and again and again to element A, which is called actually generator of the group. So A1 time it's A squared is E, A by power 3 is A by power of 4. What would it be? E, of course E, because A squared, right? So, and we go in circles. So, you see that this group is exactly circle.
binary numbers.
Eh?
Would they be sort of binary numbers?
So, this group are called circular because it's all comes in circles. Actually, you may try to look at the groups more complex, like E, A, and, for example, separated from this, like A squared, but A squared is different. So it's nothing like E, not that. A group of 3 elements, E, A, and A, and find out what is going on with this group. One just small thing, that this element which you have, like element A, right, and the element B, which gives group unit, this element B is called A by the power of -1. Do you are familiar with minuses, the power minus
Yes.
power?
No.
A to the power of minus, like minus n, right? It's 1 divided by A to the power of n. This is definition of negative powers.
Oh, 1 divided by 8 times the power of n.
1 divided by A to the power of n. If you have negative. Just negative power means this. That's all. It's definition. So.
Plus is the minus of. It's the opposite of plus. So instead of multiplying, you would divide. Yummy.
Yeah, divided. A to the power of -n equals 1 divided by A to the power of n. It is plus n. Here is minus n. This is definition. So A to the power of -1, by this definition, it is 1 divided by A. And this is called inverse element. It's back, remember? Transformation here, transformation back. Transformation back is A to the power of -1. Of course, if you A multiply by 1 divided by A will be just 1, right? Or E. Okay.
Yeah, that makes sense.
So that's I think more than enough for today. Any questions on this?
No. No extra no.
Okay. So just think about all this. Talk to your daddy, and we'll talk when you come here. We'll maybe talk like more seriously on all of that. Okay.
Okay, thank you, Jada.
Okay, you're welcome, guys. See you soon.